All right, science fan, we're going to be doing the molecular model kit lab today, and we're going to start by using the molecular model kits, and every color here represents a different element. So we're going to start with water, H2O, and if you guys did your dot diagram, you know that they're single bonded hydrogens to an oxygen. So we're going to use yellow for hydrogen and red for oxygen. Since it's going to be single bonds that we believe, we're going to take 2 sticks. By taking 2 sticks, that's going to create our single bond. So if you notice in oxygen, there's actually 2 holes. So these model kits take into account the sharing that should occur. And when we put this together, oxygen is red and 2 hydrogens are yellow. We end up getting this shape for our molecule of water. So now that we put that together, these model kits actually create the real shape that the molecules form. So when I draw this, I need to draw it as a ball and stick model. So I'm going to draw it with my oxygen in the middle, single bond to the hydrogens. So when we do the ball and stick model, we're simply not showing if there's single, double, or triple bonds, and also the shape. So this is the shape and you are going to draw in your lab. It's going to be 1 oxygen single bonded with 2 hydrogens, oxygen in the middle, hydrogens on the end, and it's in that bent shape. Go ahead and write that down. We'll try the next one. Next up is ethyne. Now ethyne has 2 carbons. Carbon is going to be the black spheres. 2 hydrogens. Hydrogens are the yellow. So I have enough of each. And it looks like we're going to put a single bond hydrogen to each carbon. So let me go ahead and do that. And then what you can see is that when we bond the carbons together, there's still 3 holes open on each of the molecules. So what I'm going to do is I'm going to fill up those holes by using the springs to make sure that every hole is filled. Whenever we do these model kits, we want every single hole filled. So in order to do that, now I have my 3 springs and I have my molecule. It looks like this is going to be a 1, 2, 3 triple bond with the hydrogen single bonded on the end. So if I were to draw that as the ball and stick model, I'm going to have my 2 carbons in the center, and that looks like I'm going to have a triple bond. So 1, 2, 3 lines to represent that triple bond, and then I'm going to have my hydrogens straight out. So there's your ball and stick model for ethyne, and if you look, this thing is straight across. It's not really bent or that, but straight. That's interesting because maybe when you drew your dot diagram, you should have had that triple bond, but did you draw it so that it was straight across? That's something we'll have to consider. Why are some molecules bent and some straight across? Up next is CH4 methane. You're going to have 1 carbon with 4 hydrogens. From our dot diagram, it looks like we're going to have 4 single bonds, and that makes sense because there's 4 holes in the carbon atom, so that means it can hold up to 4 single bonds. Each hydrogen only has 1 hole because it only wants 1 single bond. So in the end, you end up with methane, which looks something like this. Kind of looks like a pyramid with a little head on the top, right? So when we draw that, we want to make sure we show that almost to look 3-dimensional. So we're going to draw the carbon in the center. We're going to draw 1 hydrogen up top, 1 hydrogen on the side, 1 hydrogen on the side, and then 1 down low to kind of give it that 3-dimensional shape, to kind of show that it has that pyramid on the bottom with a little head on top. But that is methane. Up next is chlorine. We can use 2 greens to represent chlorine, and each green, because it's a halogen, only has 1 hole. Put them together, and it's actually a simple single bond. So the way we would draw that for the ball and stick model is there's going to be 2 spheres with a single bond, and these are both chlorine. So there you go. You have your straight across chlorine molecule. Go ahead and write that down. Here's ammonium, and normally we use a blue sphere for ammonium, but since we have 4 things on it and has a charge, we're going to actually use black for carbon because it needs to have 4 bonds available to it. So what we're going to do is the nitrogen is going to have 4 individual bonds, and each one is going to be hydrogen. So this has ended up looking quite a bit like methane. Because of that positive charge, remember that it ends up being 1 less electron. So nitrogen is going to be in the middle. There's my ball and stick model. 1 hydrogen up top. 1 hydrogen off to the side, so it's kind of that pyramid shape again with a head on top. But there is your NH4 plus 1 or ammonium ion. Up next is HF, hydrogen fluoride or hydrofluoric acid. Hydrogen's yellow, single bonded to fluorine, all the halogens we use for green if we'd like. And that becomes a very straightforward molecule. So, we put it this way, hydrogen's first with a single bond to fluorine. The ball and stick model is just simply H single bonded to F. Write that down. Next we have hydrogen gas. Hydrogen gas will be 2 yellows. They each only have 1 hole in them, so there'll be a nice single bond between them. So for my ball and stick model, hydrogen is going to be 2 spheres with the single bond. Go ahead and write that down and see if that's close to your electron dot diagram. Dichloromethane is next. This one's fun. Actually, carbon's going to be in the middle. You're starting to see maybe carbon loves being surrounded by 4 different bonds. So it has CH2 and Cl2. So there's going to be 2 hydrogens, the H2, and then 2 chlorines. We'll use green for chlorine, and chlorine each has 1 hole. So in the end, you take a look at that. It looks a lot like methane, but instead of having 4 hydrogens, it has 2 hydrogens and 2 chlorines. So when we draw that ball and stick model, chlorine's going to be in the center. There's going to be 2 hydrogens coming off of the carbon, and there's also going to be 2 chlorines coming off of the carbon. So in the end, we just want to make sure it looks almost 3-dimensional to show like that pyramid bottom with that head on top. A lot like NH4 and CH4, a similar shape. Go ahead and write that down. Next is nitrogen. Nitrogen, if you did your dot diagram correctly, you should have noticed that nitrogen connected to another nitrogen gives off is connected by a triple bond. I guess gives off isn't the right answer. So what I'm going to do is I'm going to put 3 springs on here and take a look. All of the holes of nitrogen are now filled up, and I have a triple bond. So how would I draw that with my ball and stick model? Well, I'd have 2 nitrogens, and it would be connected with a triple bond. So 1, 2, 3. Now that represents my triple bond nitrogen, and I should be all set. Go ahead and write that down. Next up is carbon dioxide, 1 carbon with 2 oxygens. If you take a look at your dot diagram, you should be having a double bond to each oxygen. That means 2 springs is going to be needed to connect the carbon to the oxygen. But there's still going to be 2 holes left on the carbon, and those 2 holes will be used for the double bond to the oxygen because the oxygen has 2 holes in it. So in the end, when this bonds together, you end up with this double bond carbon to oxygen double bond. So to draw that, notice that it's straight across. Carbon dioxide has carbon in the center with oxygens on the outside, and that's double bonded. So there you go. Now double bonded, straight across carbon dioxide. Up next is a fun one. We've got methanol. And if you look, carbon loves to be in the center with 4, but there's 3, 4, 5 things. So this might throw you off at first when you're doing your dot diagram. But first I'm gonna start with carbon getting those 4 single bonds. Carbon seems to really like that. Now it says we have 3 hydrogens, so let me connect my 3 hydrogens. Each hydrogen is yellow. And then my last opening spot, I've got an O and an H. Notice the hydrogen here isn't with the original hydrogen. So I think this hydrogen is going to be stuck on that oxygen. So I'm going to take red for oxygen, and I still have 1 open hole in oxygen, and I'm going to put that last hydrogen on there. And here I go. I have methanol. It's a type of alcohol. Notice the "all" in it for alcohol. But methanol is actually a methane molecule like you built. But instead of the last one being a hydrogen, you have an OH off of it. Anything with an OH off of it is usually an alcohol. But anyways, it looks like that pyramid with the head and then a little yellow, maybe like a little duck or something like that. Anyways, let's draw that ball and stick model. So we still have carbon in the center. We have 3 hydrogens coming off of it, right? Let me put that last hydrogen here to show like that pyramid. Then I've got the oxygen coming off on top with a hydrogen as well. So if you cover that up, that last hydrogen, it looks a lot like what methane and NH4 ammonium looked like. If you cover this part up, this looks bent, almost like that water originally. So we've got some different shapes here. But in the end, our ball and stick model is showing that everything is a single bond. That should be the case. H2O2 is next, which is hydrogen peroxide. That's the stuff you pour on a cut sometimes to clean it out. We're going to have 2 oxygens in the middle because we know that each oxygen is going to need a hydrogen single bonded at the end. Hydrogens love being in the end. So when I put this together, all I have left really is 1 hole in each oxygen. So it must be a single bond. So when they come together, you'll see like this. I'm going to twist it because actually these hydrogens would want to be as far away from each other. They both have electrons, so they'll want to switch like that. But in the end, this is all just a single bond, hydrogen peroxide. So you have oxygens in the middle, and then you have hydrogens single bonded on the outside. So there's your ball and stick model for hydrogen peroxide. Single bonds, and it twists and turns a little bit. Interesting. Next is oxygens. We have 2 oxygens, and there's 2 holes. All holes need to be filled in, so I'm guessing this is going to be a double bond. And if you look at your dot diagram, you should already have it written as a double bond. If you don't, you did your dot diagram wrong, because these model kits do not lie. There you go. You've got 2 oxygens connected with a double bond. So therefore, ball and stick model, oxygen, oxygen, double bond. Take a look and see if your dot diagram matches that. Go ahead and write down your ball and stick model. For our last one, we've got H2S, so 2 hydrogens and 1 sulfur. Sulfur is also red because it has similar valence electrons to oxygen, so oxygen and sulfur would be the same color. All right, if we're going to do this, the red sphere only has 2 openings, and we're going to connect it to 2 things. So I think that leaves us very little wiggle room here. There must be a single bond to each. Looks a lot like H2O, and that's no coincidence. That's real because oxygen and sulfur have similar valence electrons. So H2S, I'm going to put the sulfur in the middle. So I've got my ball there, single bonded to hydrogen, single bonded to hydrogen. Now I have my ball and stick models for that. Now, after drawing the ball and stick models, you should go back and make sure that all of your single and double bonds work out correctly when you did your dot diagrams. For example, sulfur here, your dot diagram should have looked like a single bond to each hydrogen. If that's not the case, then your electron dot diagram is off. So double check to make sure that all of your different electron dot diagrams match the ball and stick model. Because if there's a double bond somewhere, but you don't have that in your Lewis dot diagrams, then you drew it wrong. Another quick recap. Again, check your electron dot diagrams to make sure they match your ball and stick model. So in this case, you would have had a triple bond between the 2 carbons with a single bond to the hydrogens. If you don't have that, then you technically don't have a triple bond, so something's wrong. This is the correct shape with a triple bond and single bond, so your electron dot diagram should be the same. So it's good to go back and make sure your ball and stick models match the same type of bonds that are in your Lewis dot diagrams. All right, Science fam, thanks for hanging in there. Great job today. And now we're getting a little bit more inclined to, hey, what shapes do these make? Next, we'll look into what are these shapes called, because the different shapes of molecules lead to different functions. Take care, Science fam.